Recording now. Uh, and so there's going to be uh, basically two portions to this. So we're going to finish the acceleration topic. Well, not the whole topic, but we're going to finish the slide deck that we started last time. Uh, last time being a fairly long time ago. Okay, so the things that we didn't. My screen is being very weird, but that one seems okay. So the things that we didn't finish were, um, well, actually, it looks like we did all through those four, and that one. it- So we're gonna kind of talk about this, and then this will continue into the next slide deck. The main thing that we're gonna do out of this slide deck is to talk about motion diagrams. But before we completely get there, as a review, you don't have to enter in the response. We can just do it out loud as a group. Um, so I have these four velocity versus time graphs. Which graphs show an object speeding up?
Top left, bottom right.
Top left is correct, and bottom left. So how do we know that this one shows speeding up? Yeah. So that strategy applies to the bottom one too. Zero is the slowest you could go, right? So if you're going away from zero, you must be speeding up. And so both of these do that. By zero, I specifically mean v equals zero, which is the t-axis. And anything coming toward v equals zero is slowing down. So that means we can't tell just from the acceleration whether we're speeding up or slowing down. We have to look at the sign of acceleration and the sign of velocity. So what was our summary result of you compare the sign of velocity and acceleration, and then based on some rule from that, you figure out if it's speeding up or slowing down.
Is it like if both are increasing, then it's speeding? No, it's not.
Increasing is not the word I would use, but I think you might be in the ballpark. So this one, we know it's speeding up. Is the sign of velocity positive or negative? Positive, right? These are all positive values, positive 2, positive 3, positive 4, positive 5. Acceleration, is it positive or negative? Positive. How do we get acceleration from a velocity graph? Exactly. So the slope, rise over run. Definitely not the derivative, because that would be calculus, and we're not doing calculus. So the slope is positive, so the acceleration is positive, velocity is positive, we get speeding up. Down here, is velocity positive or negative? It's negative, and we can see that by reading off the numbers, right? We're -2, -3, -4, -5. All those are negative values, so the velocity is negative. What about the acceleration? Is it positive or negative? We look at the slope, so it's negative. So this one has positive acceleration and positive velocity, and it's speeding up. This one has negative velocity and negative acceleration, and it's also speeding up. So the rule just is if they have the same sign, we're speeding up. And then we can see over here, positive v but negative a. Down here, negative v but positive a. They have opposite signs, we're slowing down. The way that we can understand this physically is the acceleration is basically the correlates to the net force. So if you've got something sliding across the ice, but on a flat part, so like in the courtyard or something, and sliding this way, but you want to slow it down, which way would you push on it? The opposite direction, right? So in our typical coordinate system, velocity would be positive, but the acceleration is negative because it's pointing that way. But if it's sliding this way and you'd like to speed it up, which way would you push it?
So,
Same way, right? So that way the velocity and the acceleration are pointing the same way, in this case, both negative, and we speed up. So that is the rule that's going to manifest throughout the entire semester. We will add additional rules to it, but that's always going to be there. If acceleration and velocity point the same way, it doesn't matter which way they're pointing. If it's the same way, we speed up, and if it's exactly opposite, we slow down. How are we feeling about that? So we are going to now look at motion diagrams. You might remember these. This is the dots and arrows stuff. So we put dots at every even interval of time. So maybe it's every 1 second, or maybe it's every 10 seconds, or maybe I don't really tell you what the numbers are, but it's every even interval of time. And then we connect the dots with the velocity arrows to tell us, you know, which way it's going, basically. And we haven't yet talked about the acceleration arrows. It is now becoming relevant, but I'm still not going to ask you to draw those yet. So what I want you to do with this, actually, maybe we'll do one together, and then I'll have you, I'll split y'all up and have you do some of the others. So let's do the easy ones so I can leave all the hard ones for you. And we'll look at positive velocity and positive acceleration. So it doesn't tell us where we need to start, so you can start anywhere you want. I'm going to start in the middle for no particular reason. And I don't think I say it, but we're going to use right as the positive direction. That's what we typically do. So if velocity is positive, which way is our object moving? In the positive direction, so that way. So the next dot is going to be somewhere to the right of our first dot. If velocity is positive and acceleration is positive, are we going to be speeding up or slowing down? Speeding up. And how do I show speeding up with the dots?
the gaps get larger.
Exactly. So I could make a gap of 1, and then a gap of 2, and then a gap of 3, and then a gap of 4, and a gap of 5, something like that. And then I just connect the dots with the green arrows. You really need to go all the way from one dot to the next dot because quantitatively we're showing the displacement here. And then I might as well show the acceleration vector. So formally, what's going on with the acceleration vector is it's telling you what you need to add to the, so I'm looking at this second dot. I can't look at the first dot because there's no velocity before it. There's only a velocity after it. So the second dot is the first one where there's a velocity before and after. And the accelerations vector is what do I need to add to the before vector to get the after vector. So if the before vector is pointing a little bit this way and the after vector is pointing a lot that way, what direction do I need to add a vector to go from a little pointing to the right to a lot pointing to the right. Do I want to add something that's pointing to the right or pointing to the left? The right. So the shorthand for this is that we already know the acceleration is pointing to the right, so you can just draw all the arrows pointing to the right. I'm not going to make a big deal out of it if you put an acceleration vector at the first and last dot, but again, formally you wouldn't, because for the last dot, there's a before velocity, but there's no after velocity, so you can't talk about how the after velocity has changed. And then the opposite with the first dot, there's an after, but there's not a before, so you can't talk about how the before vector has changed. I don't pay particular attention to how long the acceleration vectors are, but they do go on each dot, or I guess, by each dot, because formally it's going in between the velocity vectors. And where do we have in between velocity vectors? We have them at the dots. Okay, so I will divide it up. Let's see, what's a good way? How about you two do the velocities negative and accelerations positive, and then you two do velocities positive and accelerations negative, and then Subi and Kate do both are negative, and then we'll start back over. So Bo and Abdisa do negative velocity, positive acceleration, and then there's an odd number of you. I guess unless you want to work alone, y'all three will do positive velocity and negative acceleration, and then the last two, this one, negative velocity, negative acceleration. So on the Pear Deck, circle the one that I've given you, and then draw the motion diagram that goes with that.
Blue dots, green light comes that way.
I
think
Which I'm wrong.
because
Maybe
we're moving.
I don't know. That's why I guess I'm gonna look over yours so that you're like, I think that's what we're supposed to do.
Yeah, but the
I
acceleration.
never really looked at it.
The rise.
Okay, because I think it's elevation. Well, yeah, because acceleration. I also like so much. So we story to me. Because the first question is like, stupid. Because that's really what we talk about. Oh, God, please. Signing up for what I think if it's going this way, the acceleration is going this way. So like sort of something. I'm just trying to be. Okay, yeah. I think that makes sense. And then, yeah, I was running with the arrows. Or something.
Okay, I think we're doing pretty well here. Let me select which one I want to start with. Uh, okay, yeah, we'll start with this one. Okay, so I'm just showing a couple here. Oh yeah, I've got to delete my annotations. Okay, so for this first one, we know that we are going left because velocity is negative, and we know that we're slowing down because velocity and acceleration have opposite signs. So the dots are going to the left, and they're getting closer together since we're slowing down. And then the acceleration vectors are pointing to the right because the acceleration is positive there. And there's just another one showing the same idea. How do we feel about that one? Okay. Let me select some for the next one. I'm just going to show this one. Actually, let me pick one where the acceleration vectors look a little bit different. Well, that's fine. Okay, but if we focus on the dots and green arrows, we know that we're going to the right since velocity is positive. We know that we're slowing down since the signs are opposite. And slowing down means the dots get closer together as you go to the right. And green arrows go from dot to dot. The orange arrows, I'm not going to make a big deal about this, but they don't need to span from dot to dot. You can just put a little orange arrow next to each of the internal dots. If you wanted the arrow to be exactly the right size, the orange arrow, it would be the difference in the tick marks. Actually, sorry, the orange arrows should point left, huh? That's right. So they, since the acceleration's negative, they should point the other way. So let me draw what I would do for the orange arrows. So I'll put them up here, like that. The dots and green arrows are more important to me than the orange arrows, but this is what those would look like. If you wanted the size of the arrow to be exactly right, what you would do is the length of the orange arrow would be the number of tick marks difference and the lengths of the green arrows. So this green arrow is 5 and this one is 4. So you would try to make it one tick mark pointing to the left. You don't have to do that, but yeah. Any questions about that? Okay. And then the last one. Oops. I meant to just have this top one here. Okay, so we have the velocity is negative, so we know we're going to the left. Acceleration is also negative, so they have the same sign, so we know we're speeding up. Speeding up means the dots get farther apart. And then the acceleration, since we know it's pointing to the left, you can put a little arrow pointing to the left by the dots. Any questions about those? Okay. So, I'm giving you 6 motion diagrams, and I want you to pick the diagram or diagrams that show a positive acceleration. So we've got the dots and the velocity vectors. We just want to know what acceleration that goes with it would be positive. A lot of people put medium faces for their happiness option at the beginning. And then several people have no faces.
Yeah, I skipped it.
Why? It's so fun. Yeah. The little pear does whatever fruits you put.
What pair?
Oh,
Like this one?
pear? Yeah,
Oh,
just crazy, but it's a pear.
I think did you pull it or anything?
Yeah, for real.
I just never pulled.
Hey, just get in the corner once in your life.
Yeah,
and all of a
and you
sudden
think
you-
think
yeah.
yours better than all of us. I knew that's inside. I don't know. I like to like analyze myself. And it's also really early in the morning, so I kind of feel groggy and I don't actually feel like it. But I don't want to
Then put that.
say it and then it's like, oh, my day starts off wrong. Like, I don't know. And just-
I won't refer you to the psych ward if you put a frowny face.
Yeah, for real.
yeah, like it's not that deep, but
It low-key makes me excited. Like I come to class and I'm like, oh, the little pear, he's gonna smile. Or he's not.
what is that? Like, can I see like the medium?
Oh,
face?
here, I'll show you. So like when you're getting on it,
Oh,
I think you got the zoom in enough.
hold on.
Bro, it's like,
Okay, when
yeah,
you're
my
getting
dad's
on it,
one.
like if I put this face, he does that face. Isn't it cute?
Oh, no, that's a good face.
Yeah.
Okay. So I think everyone has their answers in. So here are the correct answers. Pretty much everyone included A. So first of all, based on the dots, is A speeding up or slowing down or going constant speed? Speeding up. based on the direction of the arrows, are we moving to the positive direction or the negative direction? Positive direction. So we're speeding up and velocity is positive. Speeding up means acceleration and velocity have to have the same sign. So that means acceleration would be positive. So pretty much everyone agreed with that. But let's look at D. So first, are we speeding up or slowing down based on the dots? Slowing down. And is velocity positive or negative? Negative for D. So we're slowing down and velocity is negative. Slowing down means acceleration has to have the opposite sign. So the opposite of negative is positive. So A and D were the correct ones there. So let's try almost the same question, only this time I want to know which accelerations are negative. Give you just a little longer. Okay. So a lot of people agreed on the correct answer, B and C. Who wants to explain why B is the correct answer?
Because it's moving in the positive direction, but it's slow.
Exactly. So the acceleration has to be opposite, which makes it negative. What about C? Who wants to explain C?
Moving in the negative direction is getting faster. So
Yep.
it has to be-
Yep. Okay. What's going on with E and F?
They're going at constant speed.
Yep. And if the velocity is constant, what does that mean for the acceleration? It's zero. Exactly. Any question about those? Okay. So up to this point, the graphs that we've seen were piecewise linear position graphs, which corresponded to constant velocity graphs. And we've seen velocity graphs that aren't constant, but are linear instead. But we haven't seen the position graphs that go with that yet. So to get there, we're going to actually start with the position graphs that are curved and see what that would mean for the velocity graph. So we're going to go in the what I think of as the forward direction from position to velocity. And then we'll talk about going back the other way. So this is definitely not calculus, so don't even worry about it. But let's say we had a function and we wanted to find the slope of that function, right? Well, if it's not a line, then it doesn't have a slope that's defined for the whole interval, right? So what we can do is start estimating the slope at a given point by calculating the slope traditionally between a pair of points. So this is what uh, some other classes that aren't related to physics in any way would call a secant line between 2 seconds and 4 seconds. And so the position values you can't perfectly get from the graph, but I just tell you what they are up here. The 4 seconds is 24, at 2 seconds it's 8. And so you do the rise over the run for that, and you find the slope of this red line is 8 meters per second. So you could say the average velocity between 2 and 4 seconds is 8 meters per second. But let's say we're most interested in 2 seconds directly. Well, we can get a better estimate of what's happening at 2 seconds by going, instead of all the way from 2 to 4, we just go from 2 to 3. And again, I have to just tell you what the numbers are, but we'd get, 15 minus 8 divided by 3 seconds minus 2 seconds. And we get an average slope between 2 and 3 seconds of 7 meters per second. So between 2 and 3 seconds, the average velocity would be positive 7 meters per second. And we can get even a little bit closer. So we go from 2 to 2.5, and we get another slope. And you can imagine this thing as the number gets closer and closer to 2. Let's just call it a limit. That seems like a good word for it. I just made that up just now. And we get closer and closer to 2 seconds. And what we would get is a tangent line. Because it's called tangent because it just barely touches our graph at 2 seconds. So it doesn't touch anywhere else in this close by neighborhood. Just hits the graph right at 2 seconds. And we could calculate the slope of a line that does that. And, in this case, it turns out to be 6 meters per second. Now, the distinction between real calculus class and what we're doing here is I won't have you literally take this limit for a function to get a function as a result. What I might have you do is estimate it. Like if I gave you, a grid for this graph, you could estimate the slope of that line, and I would hope you get somewhere around 6. But it'd be an estimate. I'd give, a window of reasonable answers for that. Here's a demonstration. Let me make sure this is on the right screen. It is. Of the same thing here. So we've got a function. Turns out to be a parabola, but that's not important at this stage. And if we go from, let's just pick an easy number of 1 second as our starting point. If we go between 1 second and 2 seconds, our graph, is going from 1 to 4 meters. And so we calculate the slope and we get 3. And we can make that closer and closer to 1 second. So if we go between, trying to do 1.5, but I missed the line. There we go. If we go between 1 and 1.5, we get a slope of 2.5. And we can keep doing this. We can keep getting closer and closer and closer and closer and closer. And what we would eventually get is a line that comes along and touches just at that blue dot. And if we looked at the slope of that line, we would get, I can't seem to move it, but we'd get 2 as the answer. So, using that idea of the tangent line, does anyone need me to describe the tangent line more? Just to illustrate it a little bit more, so let me first turn it off again, and I'll turn these off too. Okay. If I were doing this by hand, the recording is not going to pick this up, but that's okay, they'll be fine. If I were going to do this by hand and try to make a tangent line at this point of -1 second, this is definitely a a skill to be developed, but basically I'm going to try to go through that dot, but not touch the line anywhere else. And so line would look, well, that wasn't great. I can do it. Hey, third try, right? And we could estimate the slope there. In fact, let's try to estimate it, right? So we've got a line that's going through -1, 1. So that's this point right here. And we just need to pick another point on that line. Bless you. So let's pick this point right here because that looks somewhat easy. So this should be -0.75. I said easy. I think it'll be fine. And the y value, meaning the position value, is 0.5. So our slope would be 0.5 minus 1, so that would be the rise going from 0.5 to 1. Or sorry, going from 1 to 0.5, since it's final minus, right? And then we do negative point, oh, no, too many decimals. Negative 0.75 minus -1. And we would get something probably. So negative 0.5 over positive 0.25. And so we'd get -2, I'm reasonably sure. And if we just go ahead and have Desmos check us, we're going to do the tangent line, and we're going to get the label, and we're going to put t at -1. And you can't quite see where it is, but it does say tangent slope equals -2. We did a pretty good job. So that's a thing that I will ask you to do just like once or twice, just so that we have this idea of how to do it. But generally speaking, I'm not going to ask you a whole lot of finding a slope of this curved function, other than the type of estimate we just did. So, looks like I forgot to change the text color. So I'm going to, what am I going to do? I'm going to go to the original slide version of this and change the text color on here. Nope. What am I doing? Do I know what I'm doing? Okay. And then I'm going to add that to this window. Okay, so this is the question. So we've got two masses. We're calling one P, we're calling one Q. And they have this position versus time curve. So Q is kind of going like this, and P is going like that. And I forgot to change that color to, there we go. Okay. And these are your options. We want to know when, if ever, P and Q have the same velocity. And you can see our options here. They have the same velocity at 2 seconds, or they have the same velocity at 1 and 3 seconds, or they have the same velocity at 1, 2, and 3 seconds, or they never have the same velocity. So I'll give you, I don't know, some amount of time. I'll give you a minute. Why not? Okay, so we have a majority vote for A. Let me go back to the. Where is my mouse? There we go. Majority vote for A, and that is the correct answer, I think. Let me just double check what the options were again. Was that one was just the 2 seconds, right?
Yes, sir.
Okay, so how can we tell? First of all, how would we get the velocity just generally? The slope, right? So P has a constant slope. So really what we have to think about is the slope of Q. So that they can see this on here. Uh, Drawing or drawings? Maybe it's drawings. Yeah. Okay. Why am I doing this to my neck? Okay, so I'm going to put this graph over here on our Google Drawing so that I can draw the tangent lines in a way that shows up in the video. So, of course, P, just the line is the tangent line. It's already a line, so we don't have to worry about it. So for Q, at 1 second, the tangent line would look something like this. Let me make that bigger, maybe even bigger. Okay, that's maybe too big now. At 3 seconds, it would look something like that. And then at 2 seconds, it would look something like that. So now that I've drawn these three tangent lines, I think Violet already said, but how do we get the velocity from these tangent lines? We take the slope, right? So this one, of course, there are no numbers on this axis, so we're doing this semi-quantitatively. But this one is clearly steeper than the slope of P, and Q is clearly shallower. And then two, for them to have the same slope, that would mean the lines are parallel. And, based on our estimated tangent line here, it's pretty parallel to P, and so it has the same slope there. So it has the same instantaneous velocity at that point. I just realized I hadn't used the word instantaneous velocity yet. And I tend not to. When I say velocity, I mean instantaneous velocity. So that means the velocity at one particular moment in time. And if I mean average velocity, I'll say the whole phrase average velocity. How are we doing? Any questions on those? All right, how much time we've got? We don't have like an enormous amount of time. And yet, um, my brain froze mid-sentence anyway. Wait, no, class doesn't. When does class end? Where am I? Who are you people?
That's him.
It ends at 10, not 9:30. Okay, I'm back on board.
Yeah, I was like, 40 minutes.
Need more coffee. Okay. So we'll go ahead and end this one. Do the takeaways. Okay. And then put this one over here. Double check that I'm still recording. Guess my camera's on, so that's a good indication. Exothermic X-rays. I guess X-rays could be, but no. When would they be exothermic? They're not really reacting. I guess you'd have photon-photon scattering between X-rays in what kind of medium would that take? I don't know. I think it'd have to be a crystalline solid. If we just had a different word than zebras here, we could make this an actual physical chemistry thing. Hmm. I'm not going to come up with another Z word, though, that works. Pretty close. All right. So, this is going to be continuing the idea of looking at position graphs when velocity is changing. But before we go there, just as a reminder, we kind of already did this reminder, but here it is in Pear Deck form. We've got two cars. Which of the two shows slowing down? Um, I didn't get the letter changed, but the one on the left is A. Okay. It is unanimous, and that is correct. What about this one? Okay. Also unanimous, at least among those who voted. And how do we know?
The opposite direction.
Exactly. Okay. So we're going to be looking at position versus time graphs first to see how can we find speeding up and slowing down in them. And then secondly, how we can actually create a position versus time graph given a velocity versus time graph. We're definitely not going to have time to get into free fall. Okay, so we've got two graphs of position versus time. There is a grid there. You don't have to numerically use the grid, but you can if you want. Based on the position versus time graph and thinking about this idea of the slope of the tangent line, which of these show speeding up? Oops. I think I just showed you the answer for a second. So people generally agree with A. How can we tell that it's speeding up?
Because the slope is
Exactly. So if I were to grab this and put it in Google Drawing. So if I draw my tangent line, and just pick a couple points on there. I guess I'll do 3 for each one. So there's a tangent line, there's a tangent line, there's, well, that's not a great tangent line, but close enough. Let me make these bigger. Okay. Is the tangent line getting steeper or not steeper?
deeper.
Yeah, exactly. And if I do the same sort of thing over here, we can see that the tangent line is getting closer to being flat. Flat would be velocity is 0, so it's getting closer to 0 velocity. So I'm going to ask you the same kind of thing for these two graphs. Here we go. I need to close that window or I'll keep getting confused. Okay, give you 30 more seconds. Okay, so among those who voted, the unanimous vote is B. So how can we tell?
It's getting like less flat of a slope, you know?
Yeah. So just to show that, if you're still working on visualizing these, put this one down here. I guess the size is probably fine. So on the, oh, interesting. Because that was, oh, it's just doing the border. Okay, never mind, not interesting. So this one has a tangent line that looks kind of like that there, and something like that. So these tangent lines are getting closer to horizontal, closer to flat. And so that one would be slowing down. Whereas the tangent lines on this one are getting gradually steeper. So the velocity is negative, but it's getting faster in the negative direction because it's getting steeper and steeper. How are we feeling about that? So these four graphs, these are portions of a parabola. So if you put this and this together, so if you put this one on the left side and then put this one on the right side, glue those together, you would get an upward facing parabola. Whereas if you put this one on the left and this one on the right, you would get a downward facing parabola. Those are going to be what we generally see in position graphs in this class. The reason is that those correspond to velocities that are linear. If you've done Cal, I think you could get it from Cal 1, but certainly Cal 2, you would see where that's coming from, but it doesn't matter if you do or don't see where that's coming from. So there's basically these four curved options for position, and then position could also be a line, either going up or going down with constant slope, or it could be constant, which is just a subset of line. So these four shapes of graphs glued together in different ways will be the position graphs that you see in this class. Velocity graphs will only be lines or constants. And when I say this, I mean piecewise. Right? We can still stick different parts together. Velocities will only be lines or constants, and that means accelerations will only be constant, piecewise constant. So we've talked about going from the velocity graph to the acceleration graph. That was last time for y'all. And we just take the slope. Going the other way, going from a velocity graph to a position graph, this is where we have to use that area technique. And last time we did this, we had velocities that were piecewise constant. So it wasn't 100% necessary to use the area. You could use some other types of reasoning to get there. But here, we're going to have to use the area specifically. So it's always going to be the area between the graph itself and the t-axis. So if the graph is above the t-axis, it's going to be the area here. And if you're looking at the graph below the t-axis, it's going to be this area here. So if you were looking, I've just told you the answer. The one additional piece of information is when the area is positive or negative, and that's just is the graph positive or negative at those points. Make sure you do use two different colors, one for the positive and one for the negative. Okay, it looks like people have broadly answered. Maybe like 10 more seconds. Okay. So here are some of the correct answers. Right, so we've got, still can't find my mouse, there it is. We're always looking at the area between the graph and the t-axis. So here, where the graph is above the t-axis, we're shading in this part, and all of this would be positive area since the graph is above the axis. When we're below the axis, we're going up to the t-axis, and since the graph is negative here, this area would be negative. Any questions about that? Okay, so what we're going to do now is actually do that calculation. So I'll do the first example or the first second with us all together. So first note that I am just declaring where we're starting at. Remember, velocity can't tell you what position is, just how position changes. So if I don't tell you a starting point, you can choose whatever starting point you want. Um, so in this case, I'm telling you we're going to start at 0. Let's see, is there a way to do this that will show up for the video? Well, I'll just try to indicate it with my mouse, I guess. So between 0 and 1 second, we want the area of the graph between, the area between the graph and the t-axis. So the graph is constant right there. So we just have a square with height 1 meter per second. These heights and widths have units, but don't worry too much about that. So a height of 1 and a width of 1, you multiply the 1 by the 1, and you get 1 meter. So our total area is 1 meter. So that 1 added to the value that we had before. So you're going to do the same sort of idea to get the value at 2 seconds. You're going to calculate the additional area between 1 and 2 seconds, and so on and so forth. While you're doing that, I'm going to see if I can find my water.
So Instagram quotes though. So
Like, not that it's really basic. You know what? Okay, so my skin. I was seeing shut down the game and stuff. It feels like that. Very like I see both sides of it. Also, I'm like sitting barely finished high school. Like I'm like doing it and really know what's going on. Like what they are so rich, so pretty. It's like none of them know what else could also I agree with you that it's like you can't have a huge popcorn in 6.
It's like, yeah, it's,
If you had to find a happy medium, but I feel like there's not one.
I think it's just like if you really you should say something about like don't like don't have an opinion. You shouldn't have to say anything. But if you want to, well, hard should be. Well, no.
They have like a group in one to say speaker.
What the fuck is
posting about it? Look at this guy's sign.
Okay, so let's talk about a couple of them together. So let's see. I'm going to again grab this, make a new Google drawing. Okay, so we talked about finding the area between 0 and 1 second. So that's that area right there. That area is 1. So our value is 1. So between 1 second and 2 seconds, we have another rectangle, well, square. So it goes from there to there. And so the area of this new square is 1. But to get the position value, we need to add that to the 1 that we already had before. So we take this one, our position is this value plus the area of this. So our position is 2 here. Nope. Hit the wrong number and it's black on black. There we go. Okay, and then Google doesn't love the shape. Actually, it looks pretty close. Here we have a triangle. Right? So what's the area of this triangle? Half. So we're going to add that half to the 2 that we had before and get 2.5. I'll do the next one with you and then have you finish it on your own. So between 3 and 4 seconds, I don't know if it's gonna like doing it this way. I'm gonna rotate it so it'll fit the way I want. There. This is the area between the graph and the axis. And what is this area? A half, but since it's below the axis, the signed area, we call it, is negative a half. So we add that negative half to the 2.5 we had before, and what did we get? 2. Oh no.
It's a beautiful picture.
It is, isn't it? That's my summer home.
Oh.
That's what it is, right?
Okay. Okay, so we'll look at the last two. Okay. So between 4 and 5 seconds, we have this portion of the graph. So that's like a triangle stacked on top of a square. Um, and so the area of this one is negative 1.5. We add that negative 1.5 to the 2 that we had so far, and we get our 0.5. And then for the final second, we have a rectangle again with a height of -2, quote unquote, width of 1. So the area is -2. We add that to the 0.5 we already had, and we get negative 1.5. So I'm going to add those values to what I have here because you'll need the values on the next slide. Come on. Okay. And what I want you to do on the next slide, excuse me, is to draw the position graph from that information. So the way you're going to do this, the way I very strongly recommend, is first put dots at each of the values that we know. And I'll bring that back up in a second, but it's these numbers. So you're going to put dots at those values, and then you're going to connect the dots with the appropriate type of graph. What do I mean by that? It's either going to be a straight line when velocity is constant, or it's going to be a curved line when velocity is changing. And so your final answer will have the dots at each 1 second interval. I've already given you the 0, 0 dot. And then the lines or curves that connect them appropriately. So here's a reminder of those numerical values. Okay, I'm going to show some of these, uh, sort of. Okay. Yeah, so you put the dots where they go. Um, I'm going to highlight this one a little bit. Now, on Pear Deck, even there is a line tool, but like distinguishing the part that should be a straight line versus a part that curves but not a huge amount, I mean it's tough. But in principle, between 0 and 2 seconds ought to be a straight line, because velocity is constant there. And then between 2 and 3 seconds, we should curve downward because we've got a positive velocity that's going to 0. Where does 0 velocity correspond to on this graph?
to 6. Oh, sorry. 3.
At 3, right? So this is when we're changing direction, right? So before 3 seconds, we're going upward or to the right or whatever. Let's just say up to make it easy. We're going upward. After 3 seconds, we're going downward. So right at 3 seconds, we're changing direction from positive to negative. And so that's going to be a maximum point there. Generally between just continuing. Between 3 and 5, we should be sloping more and more downward because our velocity is negative and getting more negative. But between 5 and 6, ideally, this part would be a straight line. And honestly, if you just connect the dots and like just by eye, you can basically get it. The shape's going to be basically right. But I do want to highlight, I want you to know where it is meant to be a straight line in case I come up with a good way to ask you a question about it. Any questions about that? One last thing, this ought to be fast because we've basically done this. So we have a velocity graph. I want the acceleration graph. How do we get acceleration from velocity? The slope. So, find the slope in each of these intervals. This is a piecewise linear function. So it's got one slope between 0 and 2, another one between 2 and 5, and the last one between 5 and 6. Okay. I'm just going to quickly show you a couple of these since we are just about out of time. We know that between 0 and 2 seconds, the velocity is flat, so that means the slope is 0. Between 2 and 5 seconds, the velocity has the same slope, and that slope is -1. So we're going to have a constant acceleration of -1 between 2 and 5 seconds. And finally, between 5 and 6, it's 0, or sorry, it's flat, so the slope is 0, so acceleration is 0. All right, feeling good. Feeling okay. Feeling goodbye. See you Friday. Wonder how much of this video they could only see my hat for my in screen camera.